Swayam Prabha. Digital India. Educated India.
Welcome to the class. We will solve some examples on regeneration. So, we are practically going to consider the Rankine cycle with regeneration or regenerative Rankine cycle during these examples. So, first example reads as a steam power plant operates on an ideal regenerative Rankine cycle. Turbine inlet conditions are 15 megapascal and 600 degrees Celsius. Condenser pressure is 10 kPa. Some steam leaves the turbine at 1.2 megapascal and enters in an open type feed water heater. Find thermal efficiency and fraction of steam extracted. So, we will start with the given things. So, in this we will first draw the Rankine cycle for us. We have to remember that this is open type of feed water heater, and in the open type of feed water heater there will be two big pumps and then so this is 1, 2, 3, 4, 5, 6 and 7. So, we will say that Y is given in the feed water heating. So, we will have 1 minus Y in the rest of the turbine and 1 minus Y in the condenser. So, given things for this example are P5 is equal to P4 is equal to P3 is equal to 15 megapascal. Then given things are P5 is equal to P4 is equal to 15 megapascal. Then P3 is equal to P6 is equal to 1.2 megapascal. Further, T5 is said as 600 degree Celsius, and here P2 is also equal to P3 and that is equal to P6. Further, P1 is equal to P7 is equal to 10 kPa. Now, in this example we will first go into the steam table corresponding to 10 kPa and find out H1. So, H1 will be the enthalpy, which is liquid saturation enthalpy at 10 kPa. So, its value is 191.81 kilojoule per kg. Similarly, we will keep on writing about new one V1, which is specific volume, and this will be 0.001010 meter cube per kg. Then we can find out here delta H P1, or which we will also call it as specific pump work. And this specific pump work, we have to remember that what we are calculating here is specific pump work, since in the process 1 to 2 there is only 1 minus Y mass in the component pump. So, it is not multiplied with mass. So, it will be V1 into P2 minus P1. So, V1 is known 0.001010 into P2 is 1200, since it is 1.2 megapascal minus 10, and this gives us value of 1.2 kilojoule per kg. So, this is value of delta HP1. Then we can find out H3 from the steam table, and H3 is liquid saturation enthalpy at 1.2 megapascal. So, this is 10 kPa and this is 15 megapascal. So, at 1.2 megapascal we can find out H3, and H3 will be 798.33 kilojoule per kg, and specific volume at the same station can be also seen, which is 0.001138 meter cube per kg. This would be helpful for us to find out the pump work in the second case, and so that is actually WP, which is pump work. Since here this Y is going to mix with 1 minus Y, and that will be total mass. So, this will be total mass. So, total pump work, and then that total pump work is nu1 into P4 minus P3. So, specific volume is known, 0.001138, it is 15,000 kPa minus 1,200 kPa, and this gives us 15.70 kilojoule per kg as the second pump work. Now, we can go into the steam table and find out H5, which is the enthalpy at station 5, and that H5 is 3583.1 kilojoule per kg. We know at 5 we have 15 megapascal pressure and 600 degrees Celsius. So, we should go into the superheated part of the steam table and find out what is the H5, but parallelly we will keep it also noted about S5. So, S5 and S5 will be 6.6796 kilojoule per kg Kelvin. Now, we know S5 is equal to S6. So, we can go into the steam table and then find out at what temperature we will have at 1.2 megapascal, same entropy as S6, and it happens to be a superheated zone at 1.2 megapascal as well. So, we can get H6 is equal to 2860.2 kilojoule per kg, and here we basically get T6 is equal to 218.4 degrees Celsius. We should also keep it in mind that we might not get, if we are using steam table, then we might not get exactly same entropy, then we have to interpolate between two entropies and find out one intermediate value, and then we would go back and then find out basically H2, which is H1 plus delta HP1, and we get H2 is equal to 191.81 plus 1.2, and this gives us H2 equal to 193.01 kilojoule per kg. Similarly, we will find out H4, which is H3 plus WP, or we can also say it as delta HP2, but this is actual pump work. So, this is WP2. So, H3 is 798.33 plus pump work is 15.7. So, it gives us 814.03 kilojoule per kg. So, once we know now this, we can find out our required mass, which is Y1, through the energy balance. And for that we can use the equation which says that Y amount of mass at state 6 mixed with the 1 minus Y amount of mass at state 2 to give 1 unit of mass at state 3. So, we know it is YH6 plus H2 minus YH2 is equal to H3. So, we have Y of H6 minus H2 is equal to H3 minus H2, and this gives us Y is equal to H3 minus H2 divided by H6 minus H2, and then we know all enthalpies. So, H3 is basically 798.33, H2 is equal to 193.01, and then we have 2860 H6 2860.2 minus H2 is 193.01, and this gives us Y as 0.227. So, this is the mass fraction. Now, we know this mass fraction, we can now calculate actual pump work also in the first pump by multiplying it to 1 minus Y. But further we can find out state 7, where we will take S6 is equal to S7. So, we will go into the steam table and we will see at what temperature or at what condition we will have the entropy at state 7 equal to state 6, and so it happens in this case that we are inside the dome. That means S6 is lesser than the vapor saturation vapor entropy at 10 kilopascal. So, S7 is equal to S6 is equal to S1 plus X into SFG. Here this will helpful for us to know it is S6 minus S1 divided by SFG. So, we can get this as 6.6796 minus 0.6492 divided by 7.499, and this gives us S7 or rather X as 0.8041. So, this is the dryness fraction at state 1. We will move here onwards and find out what is the amount of heat added and what is amount of heat rejected. So, amount of heat added Q in is equal to H5 minus H4. We know H5 as 3583.1 minus 814.03. So, this gives us Q in is equal to 2769.1 kilojoule per kg. Similarly, Q out is equal to H7 minus H1, but this is not for 1 unit of mass, this is for 1 minus Y kg of mass. So, this will be 1 minus 0.227 into H7 is 2115.3 minus 191.81. Here, knowing the dryness fraction, we would have calculated H7, which is equal to H1 plus X into HFG. Basically, this H7 is only used by us, where H1 is 191.81 plus X, and this X is 0.227 into HFG, which is 2392.1, and this gives us 5.3 kilojoule per kg. So this H7 is used over here to find out Q out, and we get Q out to be 1486.9 kilojoule per kg. So efficiency is equal to 1 minus Q out upon Q in. So Q out is equal to 1486.9 and Q in is 2769.1, and this gives us efficiency as 46.3%. So here we have to remember one point, that we are using different masses which are present in the different components of the circuit to find out individual interactions, and this we do not have to forget in the case of regeneration examples. So we will proceed with next example, and next example states that there is a steam power plant based on regenerative cycle. Steam enters the turbine at 400 degrees Celsius and 3 megapascal state, while the condenser pressure is 10 kPa. Find cycle efficiency and mass fraction extracted at 0.6 megapascal for open type of feed water heater. So we are given again in this example that there is open type of feed water heater. So we will again put the same diagram where we have all the time whenever we draw diagram, this is an intuition based diagram. This diagram would get corrected based upon the answer. For the example, this point 6 we are having at this moment inside the dome, but this might be inside or might be outside the dome. So this is y, this is 1 minus y. So this is 3 megapascal, this is 0.6 megapascal, and this is 10 kPa. Knowing this, we can say what is given in this example, and in the given thing we have P4 is equal to P5 is equal to 3 megapascal, we have P2 is equal to P3 is equal to P6 is equal to 0.6 megapascal, we have P1 is equal to P7 is equal to 10 kPa. Further, T5 is given as 400 degree Celsius. So we will start, we will find out H1, which is liquid saturation enthalpy at state 1, which is 10 kPa, and H1 happens to be 191.83 kilojoule per kg. Specific volume at state 1 is 0.001010 meter cube per kg, and then we have actually delta H pump 1 or specific pump 1 work is equal to nu 1 into P2 minus P1. So it is 001010. P2 is 600 kPa minus 10 kPa, and this gives us the specific pump work for first pump, which is 0.5959 kilojoule per kg. So this is the first pump work. Now we can find out H3, which is liquid saturation enthalpy at state 3 or 0.6 megajoule per kg, and this is H3 is equal to 670.56 kilojoule per kg. Similarly, specific volume at state 3 is equal to 0.001101 meter cube per kg. So we can find out second pump work WP2, which is also specific, but here we are handling complete mass, which is 1 unit, and this is equal to nu 3 into P4 minus P3. So it is 001101 into P4, and P4 is 3000 kilopascal minus 600 kilopascal. So this gives us second pump work as 2.6424 kilojoule per kg. Now we can use these two pump works or specific pump works to find out other enthalpies. So H2 is equal to H1 plus delta HP1. So H2 is 191.83 plus 0.5959, and this gives us H2 as 192.43 kilojoule per kg, and H3 is already found out. So H4 is equal to H3 plus WP2, and this is basically 670.56 plus 2.6424, and then this gives us H4 as 673.2 kilojoule per kg. So now we can go into the steam table, find out H5 at 3 megapascal and 400 degrees Celsius. So we have H5 as 3230.9 kilojoule per kg, but we will also note down S5, and S5 happens to be 6.9212 kilojoule per kg Kelvin. After this we will find out state 6, where we have S5 is equal to S6, and then for that we will have to go into the steam table, find out at what temperature of 0.6 megapascal we will have same entropy as that of S5. So we can get from here H6 basically, and H6 turns out to be 2829.63 kilojoule per kg. So for this T6 is 190.97 degrees Celsius. Keep this point in mind that we might have this T6 point inside the dome if we would have the vapor saturation entropy to be higher than the S5 or S6. In that case 6 would have been inside the dome, but at this moment we have vapor saturation entropy to be lower than S5. So 0.6 is in the superheated zone. Then we got everything necessary which is required to find out the mass fraction. We can know now, directly use the formula Y is equal to H3 minus H2 divided by H6 minus H2. So this gives us H3 is equal to 670.56 minus 192.43 divided by H6 is 2829.63 minus 192.43, and this gives us 0.181. So mass fraction is found out. Upon that we will find out state 7, where we know S6 is equal to S7, and this is equal to again S1 plus X7 into SFG if we have entropy at 6 is lower than the vapor saturation entropy corresponding to 10 kPa, which happens to be the present case. So, X7 is equal to S7 minus S1 divided by SFG, and then this gives us X7 is equal to 6.9212 minus 0.6493 divided by SFG, which is SG 1502 minus SF 0.6493, and this gives us X7 as 0.836. Now, this will be helpful for us to find out H7, and H7 is equal to H1 plus X7 into HFG. So, H1 is 191.83 plus X7 is 0.836 into HFG, which is HG 2584.7 minus HF 191.83, and so H7 turns out to be 2192.22 kilojoule per kg. Now, we can find out efficiency of the plant, and so for that we need to find out Q in, and Q in is equal to H5 minus H4, which is 3230.9 minus H4 673.20. We should remember here the heat added is in between these two states, which are H5 and H4, where H5 is the enthalpy at the outlet of the boiler and H4 is the enthalpy at the inlet to the boiler. So, H5 we had already found out, which is 3230, and H4 also was already found out as the 673.2. Knowing this, we can get Q in, and that Q in is equal to 2557.7 kilojoule per kg, and Q out is basically as what we did in last time, 1 minus y into H7 minus H1. So, we know Q out is equal to 1 minus 0.181 into H7, which is 2192.27 minus H1 191.83. So, we get Q out as 1638.36. So, we can say efficiency is equal to 1 minus Q out upon Q in. So, 1 minus 1638.36 kilojoule per kg divided by 2557.7. So, this gives us efficiency as 30.9 percentage, and then this has helped us in finding out the parameters which were asked, like mass fraction and efficiency of the cycle. So, we will move to the next example. Next example reads that consider a steam power plant that operates on an ideal reheat regenerative Rankine cycle with one open feed water heater, one closed feed water heater and one reheater. Steam enters the turbine at 15 megapascal and 600 degrees Celsius and condensed in the condenser at pressure 10 kPa. Some steam is extracted from the turbine at 4 megapascal from the closed feed water heater, and the remaining steam is reheated at the same temperature to pressure to 600 degrees Celsius. The next example reads that Consider a steam power plant that operates on an ideal reheat regenerative Rankine cycle with one open feed water heater and one closed feed water heater and one reheater. Steam enters the turbine at 15 megapascal and 600 degrees Celsius and is condensed in the condenser at a pressure of 10 kPa. Some steam is extracted from the turbine at 4 megapascal for closed feed water heater, and the remaining steam is reheated in the same pressure to 600 degree Celsius. The extracted steam is completely condensed and is pumped to 15 megapascal before it mixes with the feed water at the same pressure. Steam for open feed water heater is extracted from low pressure turbine at a pressure of 0.5 megapascal. Determine fractions of steam extracted from the turbine as well as thermal efficiency of the cycle, and then assume TTD at 0 degree Celsius, and this is for the closed feed water heater. So, we will first plot TS diagram for the power plant which is given to us, and as per this we will have one So, this is first pump, this is condenser 1 to 2, 2 to 3, 3 to, after the closed feed water heater we will have 3 to 4, and then TTD 0 degree Celsius. So, 5 will be at same temperature as here. So, this is 6 to 7, and then in between there will be 8. And then we will have 9, then we have 10 here, we have 11, then 12, then 13. So, we will pretend that here Y steam is extracted and here Z steam is extracted. So, here 1 kg of steam is expanded, here 1 minus Y kg of steam is expanded, here 1 minus Y minus Z kg of steam is extracted, and then both the temperatures are same. So, T5 is equal, T9 is equal to T11. So, in this example we need to go first into the steam table and note all the enthalpies whatsoever given as per their state values, like as per their pressures and as per their temperatures. So, first we will go into the steam table, first given things, and as per the given things we have P9 is equal to P7 is equal to P5 is equal to P4, and everything is 15 megapascal. Then we are having P10 is equal to 4 megapascal. So, P10 is 4 megapascal, and then we have which is also is equal to P11. So, but P12 is 0.5 megapascal, and then that is why it is equal to P3, and that is equal to P2, and similarly P1 is equal to P13 is equal to 10 kPa. So, this is what the condition. So, here we are having 15 megapascal, here we are having 4 megapascal, here we are having 0.5 megapascal, here it is 10 kPa. Having said this, now we can proceed further and then the given things are further T9 is equal to T11 is equal to 600 degrees Celsius. Since TTD is 0, we are also told that T5 is equal to T6. So, with this we will first find out all the enthalpies at the different corners from the steam table. So, which enthalpies we can find out first? We can find out enthalpies which are H1, H3, H6, H9, H11. We can find out these. So, here we will get H1 is equal to 191.81 kilojoule per kg. This is corresponding to 10 kilopascal condenser condition. Then we have H3 is equal to 640.09 kilojoule per kg. Then we have H6, and H6 is equal to 1087.4 kilojoule per kg. Then we have H9, and H9 is turbine inlet, and H9 is the enthalpy which is 3583.1 kilojoule per kg, and then that is equal to H. Temperatures are same, so H11 is 3674.9 kilojoule per kg. Now we know enthalpy 1, 3, 6, 9 and 11. Basically, since TTDs are same, we can as well take the enthalpy of state 5 as enthalpy of state 6. This is the one condition what we can do. So, we can say H5 is equal to H6. So, the state 5 is so close to the state 6. So, we can make an assumption for TTD 0 as H5 is equal to H6. This is one way to solve the example where we can just make use of steam table, and then we can go ahead and we can monitor few more things where we will monitor new specific volume at state 1, and this will be helpful for us to find out delta HP1, which is the change in enthalpy in pump 1, and that is nu 1 into P2 minus P1, and we get it as 0.49 kilojoule per kg, and this gives us H2 which is equal to H1 plus delta HP1, and we get H2 as 192.30 kilojoule per kg. Then we can find out what is delta HP2, which is nu 3 specific volume 3 into P4 minus P3, and this gives us the 15 megapascal minus 0.5. So, 500 kilopascal into specific volume. So, we will get delta PH2. We can carry forward from here and we can get delta PH2, which is 15.84, which will be helpful for finding out H4, which is H3 plus delta HP2, and this gives us H4 as 655.93. Now we have H4. So, knowing all these things, now we can move ahead and then find out H7 also. So, for that we can get delta PH3, which is specific volume at 6 minus into P7 minus P6, and this gives us value of delta H P3 is equal to 13.77 kilojoule per kg. So knowing this, we can find out H7, which is H6 plus delta HP3, and so we get H7 as 1101.1101.2 kilojoule per kg. Now knowing all this, we can find out now Y and Z. So for this, we can go ahead and write down the expression for Y. For Y, we know that we can use the energy balance. So keeping this in mind, first we can find out Y, and for Y we know that Y amount of mass at enthalpy 10. If we go back, we know that Y amount of mass at enthalpy 10 loses its enthalpy till 6, such that 1 minus Y amount of mass at enthalpy 4 rises its enthalpy till 5. So Y amount of mass at enthalpy 10 is going to Y amount of mass at enthalpy 10 is going to lose its enthalpy till 6, such that 1 minus Y amount of mass would rise its enthalpy from H4 to H5. So this was giving us Y at H10 minus Y at H6 is equal to H5 minus H4 minus Y at H5 plus Y at H4. So we can have Y at H10 minus Y at H6. We can rather put it in this way, 1 minus Y into H4 minus plus 1 minus Y into H5. So we will have it as Y into H10 plus 1 minus Y into H4 is equal to 1 minus Y into H5 plus Y into H6. Further, if we rearrange all the terms, we will get Y is equal to H5 minus H4 divided by H10 minus H6 plus H5 minus H4. So if we put all the enthalpies, we will get Y is equal to 0.1726. Then we can find out Z, and this Z can be found out from again the fact that we have the Z amount of mass at enthalpy 12 loses its enthalpy to 3, where 1 minus Z, 1 minus Y minus Z amount of mass will raise its enthalpy from 2 to 3. So we can write down the same thing in terms of Z, where we will have Z at H12 plus 1 minus Y minus Z at H2 gives us 1 minus Y at H3. So Z amount of mass at H12 is again having it exchange of heat with 1 minus Y minus Z at 2, such that we will get 1 minus Y at 3. So knowing this, we can write down for Z, it will be 1 minus Y into H3 minus H2 divided by H12 minus H2, and this gives us Z to be 0.1312. So here we would have found out H12, basically H12 with the constraint that S12 is equal to S11 and we would go to the in 0.5 megajoule in pressure, we will go to the superheated part and see at what temperature we will have S11 matched with S12, such that we would have H12 is equal to 3014.8 kilojoule per kg. Similarly, we would also keep it noted for 13, where we will have S13 is equal to S11 is equal to S12. We will go to 10 kilopascal pressure and see at what condition we will have same entropy. So, from that we can get H13 and H13 will be 2335.7 kilojoule per kg. Thus, we know all enthalpies. Now, we can do rest of the calculations, where we just need to know one more thing, that we need to know what is enthalpy at 8. So, for that we know enthalpy at 5, mass at 5, we know enthalpy at 7 and mass at 7, and that we can do here. So, we know Y amount of mass at 7 is mixed with 1 minus Y amount of mass at 5 to give H8. So, Y amount of mass at 7 plus 1 minus Y amount of mass at 5 gives us H8. So, H8, knowing Y, H7, H5, we can get H8, and H8 remains to be 1089.8. Now, knowing all the enthalpies, we can find out Q in, and Q in is basically in the H9. There are two cases where we are having heat addition. So, here from 8 to 9 we are having heat addition in the boiler, and from 10 to 11 we are having heat addition in the reheater, but 10 to 11 we are having only 1 minus y amount of mass, but in the boiler we have 1 amount of mass. So, it is 1 into H9 minus H8 plus 1 minus y into H11 minus H10. If we put all the enthalpies and y, we will get Q in as 2921.4 kilojoule per kg. Similarly, we can find out Q out, which is 1 minus y minus z into H13 minus H1. We know y, z, H13 and H1. We can find out Q out, and it turns out to be 1485.3 kilojoule per kg. So, it is helpful for us to find out efficiency, which is Q out upon Q in. So, Q out is 1485.3 divided by Q in 2921.4. So, we get efficiency of the cycle as 49.2%. So, this is what we are trying to calculate. Here we used the concept of TTD, where we made use of steam table to find out H5. It is not necessary we have to use steam table, we can as well use water table to find out the enthalpy at 5. We will move to the next example. This example states that there is a steam turbine power plant which operates on an ideal reheat regenerative Rankine cycle with one open feed water heater, one closed feed water heater and one reheater. The TS diagram we will draw. The steam enters the turbine at 3 megapascal and 400 degrees Celsius and exhausts at 10 kilopascal. Some steam is bled from the turbine at 1 megapascal for closed feed water heater, and the remaining steam is reheated to 400 degree Celsius. The bled steam is completely condensed in the heater and is pumped to 3 megapascal before it mixes with the feed water at the same pressure. Steam for the open feed water heater is bled from the low pressure turbine at 0.6 megapascal pressure. Determine mass fraction of the steam bled at 1 megapascal and also find out thermal efficiency. Assume TTD to be -1 degree Celsius. So here we will first draw the steam, the TS diagram. So this is 1, 2, 3, 4, then we will say -1 degree Celsius. So this is above here, so this is 5, this is 6, this is 7, 8, 9, 10, 11, 12. 12, 13. So these are the states. So given in this example is basically this pressure is 3 megapascal, this pressure is 1 megapascal, and this is 0.6 megapascal, and this is 10 kPa. So this is what it is given, and then further given thing that this temperature is given as 400 degree Celsius. So for this we mention the given things where we have P9 is equal to P7 is equal to P8 is equal to P5 is equal to P4 is equal to 3 megapascal. Then P10 is equal to P6 is equal to 1 megapascal, and then we have this also equal to P11. Then we have P12 is equal to P3 is equal to 0.6 megapascal. P13 is equal to P1. Here this is also equal to P2. 10 kilopascal. Then we are told that T5 is equal to T6 plus 1 degree Celsius. We are also told that basically T9 is equal to T11 is equal to 400 degrees Celsius. So knowing this, we can proceed with this example. As we did earlier, we will mention all the known enthalpies, which are H1, H3, H6, H9, H11, and at H9 and H11 we will also keep mentioned S9 and S11. So we will have H1 to be equal to 191.83, we will have H3 to be equal to 670.56, and then we have H6 to be equal to 762.81 kilojoule per kg all have same units, and then we have H9 as 3230.9 kilojoule per kg, H11 as 3263.9 kilojoule per kg. So we have H9 and H11 mentioned along with their S. We would also keep mentioned S9 and S11. Knowing these enthalpies, we can find out first delta HP1, which is equal to nu 1 specific volume 1 into P2 minus P1, and this turns out to be 0.596 kilojoule per kg. This gives us H2 is equal to H1 plus delta HP1, and we get H2 is equal to 192.43 kilojoule per kg. Then delta HP2, that is the enthalpy rise by second pump, is equal to specific volume at 3 into P4 minus P3. So considering this, we get it as 2.64 kilojoule per kg. This is helpful to find out H4, which is H3 plus delta HP2, and this gives us H4 as 673.2 kilojoule per kg. Then we can find out delta H P3, which is specific volume at 6 into P7 minus P6, and this gives us the value of H7 delta H P3 as 2.25 kilojoule per kg, and we can get H7 as H6 plus delta H P3. So H7 will be 765.06 kilojoule per kg. So we have got most of the enthalpies. Then we will also mention the other enthalpies as H9, and H9 is 3230.9, which is mentioned. So for this we can go and see for 1 megapascal case at what temperature we have S9 is equal to S10, and record the enthalpy at S10, which would come out to be 2827.38 kilojoule per kg. Similarly, we can keep a track of S11 is equal to S12 and then mention S12, which will be 3117.06 kilojoule per kg. Similarly, we have S13 is equal to S12. This also gives us H13, and that is 2366.24 kilojoule per kg. So knowing this, we can find out the fraction of masses as what we generally mention. This is Y, so this is 1 minus Y, this is Z, so this is 1 minus Y minus Z, this is also 1 minus Y minus Z. So for this we can go ahead and do the calculations. We know now formula for the Y is equal to H5 minus H4 divided by H10 minus H6 plus H5 minus H4. We know how we are going to arrive at this formula. This is just the energy balance, where we are saying that Y amount of mass is losing its enthalpy from 10 to 6. So, basically y amount of mass losing its enthalpy from 10 to 6, and this enthalpy is used to rise the enthalpy of 1 minus y amount of mass from H4 to H5. Basically it is H4 to H5, so H5 minus H4. So, this is the energy balance. So, for this energy balance, we with this formula for Y, we can put all enthalpies and get Y as 0.0424. Similarly, for Z, we know the formula Z is equal to 1 minus Y into H3 minus H2 divided by H12 minus H2, and this again can be written in terms of energy balance as the Z amount of mass is losing its enthalpy is mixed at 12 enthalpy with 1 minus Y at 2, 1 minus Y minus Z at enthalpy 2, such that we will get 1 minus Y at 3. So, this is the balance for the energy balance for the other feed water heater. So, knowing this, we can as well find out Z, and Z turns out to be 0.1566. So, now this is how we have found out the mass fractions. So, now next turn is to find out what is the enthalpy at state 8. So, for that we know that we can write down that 1 minus Y amount of mass at state 5 mixed with Y amount of mass at 7. So, it is 1 minus Y amount of mass at state 5 mixed with Y amount of mass at 7 to give H8. So, this we can use to find out H8. So, H8 is equal to basically Y into H7 plus 1 minus Y into H5, and we can get H8 is equal to 764.57 kilojoule per kg. And this is required for us to find out Q in. So, Q in is equal to H9 minus H8, which is in the boiler, plus in the reheater, which is 1 minus Y into H11 minus H10. Putting all the numbers, we get Q in as 2884.34 kilojoule per kg. We can find out Q out, which is 1 minus Y minus Z into H13 minus H1, and we get Q out as 1741.70 kilojoule per kg, and this gives us an efficiency which is 1 minus Q out upon Q in. So, it is 1 minus 1741.70 divided by Q in, which is 2884.34. So, we get efficiency is equal to 39.6%. So, this is how we saw that how to solve the examples which are for open feed water heater or closed feed water heater of forward type or regeneration plus reheat cycle. We will go to the next example, which reads that consider a steam power plant operating on the ideal regenerative cycle with one closed feed water heater. The steam enters the turbine at 3 megapascal and 400 degrees Celsius and condensed in the condenser at a pressure of 10 kPa. Some quantity of steam is extracted from the turbine at a pressure of 0.6 megapascal and enters into the open. The example reads that consider a steam power plant. Example reads that consider a steam power plant operating on an on the ideal regenerative cycle with one closed feed water heater of forward type. Steam enters the turbine at 3 megapascal and 400 degrees Celsius and is condensed in the condenser at a pressure of 10 kPa. Some quantity of steam is extracted from the turbine at a pressure of 0.6 megapascal and enters the feed water heater. Compute the fraction of the steam extracted from the turbine and the find thermal efficiency of the cycle. Assume TTD to be 0 degree Celsius. So, for this again we will first draw the TS diagram. This is 1, this is 2, we will say this as 3, this as 4. So, after feed water hit, so this is after feed water heating we will reach a state 5 and then basically this state is 5 after mixing and feed water heating, and then we have 6, 7, 8, and here we are saying that the feed water heating has led to the state 9. So, in this case what is given, and it is 3 megapascal, this is 0.6 megapascal and this is 10 kPa. So, these are the things which are given. So, P6 is equal to P4 is equal to P5 is equal to P9 is equal to P2 is equal to 3 megapascal, and we will have P7 is equal to P3 is equal to 0.6 megapascal, and we have P1 is equal to P8 is equal to 10 kPa. Further, T6 is given as 400 degree Celsius. First we will go into the steam table, and again we will see some enthalpies which are directly obtainable from the steam table. So, here first we will get enthalpies like H1, H3, H6, and then we can get enthalpy. Along with that we can get entropy also. So, H1 would be here, and then that H1 is 191.83, which is liquid saturation enthalpy at station 1 corresponding to 10 kPa. H3 is equal to 670.56, and then H6 is equal to 3230, all are in unit kilojoule per kg, 3230.9 kilojoule per kg. So, knowing this, we can do one more thing. We can write down S6, and S6 would happen to be the entropy at station 6, and to find out state 7 we know S6 is equal to S7. So, from this constraint we would have monitored S6 into the steam table at state 6. So, corresponding to 3 megapascal, which happens to be in the superheated zone. Similarly, we will go into the 0.6 megapascal case and find where we will have same entropy, and then it happens to be at again superheated state, and then that is why we get H7 as 2829.63 kilojoule per kg. Now, having said this, we can go ahead and find out same way S8 is equal to S6 again, and so from that we can get the enthalpy at state 8. Here we again need to see whether this 8 point is having entropy higher than the gas vapor phase enthalpy or lower than the vapor phase and saturation vapor phase enthalpy, and accordingly we would have to calculate dryness fraction if it is lower, and then we ultimately need to find out H8, and H8 comes to be 192.27 kilojoule per kg. So, once this is done, then we can go and find out H2. For that we can say H2 is equal to H1 plus delta HP1, where we know delta HP1 is equal to nu 1 into P2 minus P1. So, we will have H2 is equal to 191.83 into nu 1 0.001010 into 3000 minus 10. So, we have H2 is equal to 194.85 kilojoule per kg. Similarly, we can find out H4, and that H4 is equal to H3 plus delta HP2. Here we have to remember that we are extracting Y mass of stream from for the feed water heating. So, this pump is forward type closed feed water heater. So, this is handling only Y unit of mass. So, we are logically saying that this is only delta HP2, this is not the pump work. So, we have H4 is equal to H3 670.56 plus nu 3 into P4 minus P3. So, we can get H4 is equal to 673.20 kilojoule per kg. Since here we would have nu 3, and where nu 3 is equal to 0.0011, P4 is equal to 3000 kPa, and P3 is equal to 600 kPa. So, knowing all this, we would find out H4. Now, we have to find out H9. So, here TTD is given to be 0, that means temperature at 9 is equal to temperature at station 3. So, as what we know, we could as well assume that H9 is equal to H3 if we would like to use steam table, or we will go to the liquid part or water part, and in those tables we can find out the value of H9. So, in this case we will write down the value of H9 obtained from the liquid water table, and that is 671.98 kilojoule per kg. We can see here that H9 is 671 and H3 is basically equal to 670. So, this is almost similar. So, knowing this, now we can find out the mass fraction extracted. So, here for mass fraction extracted, we know here what is happening, that Y amount of mass is losing its enthalpy from H7 to H3 and giving it to 1 minus Y unit of mass to gain its enthalpy from H2 to H9. So, knowing this, we can write down the expression for Y, which happens to be H9 minus H2 divided by H7 minus H3 plus H9 minus H2. So, here we can get, we know now H9 which is mentioned over here, H2 is also known, H7 is found out, so H3 is also known. So, we can find out Y, and Y happens to be 0.181. So, 0.181 fraction of 1 kg of mass is extracted for the closed feed water heating. So, knowing this, we can go ahead and then we can do rest of the calculations. So, in the rest of the calculations, we basically have to find out what is the enthalpy at state 5. So, for enthalpy at state 5 it is simple, we have to say here that 1 minus y of water at state 9 is mixed with y state of water at enthalpy 4 with y mass of water at enthalpy 4 to give 1 kg of water at state 5. So, we know now y, we know H9, H4. So, using this we can find out our H5. So, 1 minus 0.181 plus into H9, and H9 is 671.98 plus 0.181 into H4, and H4 is 673.20. This gives us H5, and which happens to be 672.2 kilojoule per kg. Now, we know enthalpies at all stations. So, we can go ahead and do the performance calculation. So, for that we will first need to find out what is Q in, and Q in, if we remember, Q in is given from 5 to 6. So, it is H6 minus H5. So, this is Q in. H6 is known, it is 3230.9 minus H5 which is 672.2, and this gives us 2558.7 kilojoule per kg. We also need to find out Q out, which is 1 minus y into H8 minus H1. So, it is 1 minus 0.181 and H8 is 2192.27 minus 191.83. So, we know that we found out H8 here using the matching of H6 is equal to H8. So, this gives us Q out, and Q out comes out to be 1638.36 kilojoule per kg. So, we can find out efficiency, which happens to be 1 minus Q out upon Q in, and then that is 1 minus 1638.36 divided by 2558.7. So, efficiency comes to be 36%. We could as well found out efficiency. For that we would need it to find out turbine work. So, turbine work we could have found out by saying that there is some 1 kg of mass getting expanded from H6 to H7. So, it is H6 minus H7 plus 1 minus y into H7 minus H8. So, this is turbine work. We would have found pump work. Total pump work is here plus here. Here we are handling 1 minus y into H2 minus H1 plus y into H4 minus H3. We know all enthalpies, we know y, would have found out W net is equal to Wt minus Wp. If we divide it by Q in, we can get efficiency. So, this is how we would have found out efficiency in the present case.